Hello, welcome to the presentation. I'm excited to introduce our recent work, Adversarial Environment Design via Regret-Guided Diffusion Models. Training agents that are robust to environmental changes remains a significant challenge in deep reinforcement learning. They often fail in unseen environments, even with a small difference from the training environment distribution. Our goal is to solve this problem by automatically generate training environments that the agent finds challenging but conducive to further improvement. We follow the framework of unsupervised environment design, UED. The original goal of UED is to obtain a minimax regret policy that is robust to the variations in the environment. To that end, UED algorithms solve the minimax problem, whose objective is a regret of the agent. They alternate between producing the training environments that maximize the current agent's regret and training the agent on the generated environments. There are two main approaches for UED. The first is learning-based methods, which employ an environment generator trained via reinforcement learning. Although these methods can directly generate meaningful environments, we observe that training the generator with RL often proves unstable in practice. On the other hand, replay-based methods achieve more stable performance by selectively replaying among previously generated environments. However, they are sample inefficient as they require additional episodes to evaluate the regret. To overcome these limitations, we propose a novel UED algorithm that leverages the power of diffusion models. First, to make UED suitable for using a diffusion model as a generator, we introduce soft UED, which augments the regret objective of UED with an entropy regularization term. By incorporating the entropy term, we can ensure the diversity of the generated environments. We also show that the modified minimax problem has a valid optimal point, so that we can learn a desired policy if it reaches the optimal point. Soft UED converts the problem of generating regret-maximizing environments into a problem of sampling the environment parameter from a softmax distribution of the regret. Inspired by the classifier guidance, we solve this sampling problem by guiding a pre-trained diffusion model with the regret. Hence, if a gradient of the regret is tractable, we can sample an environment parameter from the desired distribution. However, the regret is intractable since we cannot access the environment-specific optimal policy. Furthermore, prior works on UED propose various methods to estimate the regret using episodic returns or temporal difference errors, but none of them are differentiable. To resolve this issue, we train an environment critic to predict a return distribution of the current policy on the given environment. We further approximate the maximum with a conditional value at risk as it converges to the maximum as a risk measure goes zero. This is an overview of the proposed algorithm, AD. After the agent is trained on environments produced by the environment generator, the environment critic is updated using the episodic results. Then, the environment critic guides the diffusion-based environment generator with the regret to produce adversarial environments. By repeating this process, the agent learns a policy that is robust to environmental changes. Since AD does not require an additional training of the pre-trained diffusion model, the ability to cover the high-dimensional environment domain can be preserved. Furthermore, it enables the generator to directly produce meaningful environments via regret-guided diffusion process. Therefore, the proposed method can be seen as having both the advantage of the replay-based methods and learning-based methods while resolving some of their limitations. We conduct extensive experiments with two tasks, minigrid and bipedal walker. To evaluate the performance, we measure the zero-shot transfer performance on challenging human-designed environments and analyze the generated curriculum. In minigrid, the results demonstrate that the proposed method consistently outperforms the baselines and successfully generates adversarial environments while preserving diversity. In bipedal walker, it still outperforms the baselines, but the complexity of generated environments gradually decrease. This result arises since the randomly generated environments are excessively challenging for the current agent. As evidence, examining the returns achieved by the agent in the generated environments reveals that all methods, except for AD, consistently yield returns of 0 or below. From these results, we can infer that the proposed algorithm generates environments that are not merely more difficult, but are conducive to the agent's learning process. Additionally, we can control the difficulty level of the generated environments after the training of the RL agent is over. It enables the reuse of the Learn Generator and Environment Critic in various applications, such as generating benchmarks with varying difficulties. Thank you for listening.